All right, let me open up, I think this real quick. All right, just so we have this. I've been referring a lot to this bridge, so I wanted to get us just sort of back in the thought process. So we're going to compute a complete set of live load distribution factors for this bridge. And if what you did on 2A is sort of the dead load stuff, what we do here is kind of the live load stuff and then combining everything together. So that's why this next homework assignment is going to take, I'm going to give you 2 weeks on. So to be clear, you know, here's our cross section. We know the girder spacing's 10 feet. We know the overhang. We know the roadway width and all of that. We also know the dimensions of the bridge or the girder. Now, as we've been mentioning, this is the positive bending region. This is the negative bending region. For what we're doing right now, the distribution factors that we get for the positive bending region and for the negative bending region are by and large going to be identical except for a few key places, okay? In other words, if I put in a list every single positive bending region distribution factor and every negative bending region distribution factor and saw which ones were different, only about 2 or 3. Like all the shear ones are going to be the same, all the deflection ones are going to be the same, the lever rule and special analysis, they're all going to be the same. Just the moment ones, because the moment ones only have that kg term in it. All right? Excuse me. All right, so one other thing, a couple other things I want to refer to. So number 1 is this. We are going to use this. I know I just said that there's not much difference between the positive bending region and the negative bending region, but we are going to need some values from this sheet. So I'm going to pull back and forth from that. So I'll try and zoom in, make sure everybody can read what I'm doing and why I'm doing it. Sound good? All right. And the last thing I'm going to do is refer to this, the spec. Okay? Now specifically, I'm in section 4, and I'm in section, more specific than that, I'm in 4.6. And you'll know you're in the right place when you start flipping through pages, and the first thing that you see is your model for the lever rule. Okay, so you'll know you're in the right place. All right? Now, just to make sure everybody's paying attention, what cross-section are we going to be dealing with? Hey, there we go. All right? Before I start doing any math, a little bit on our ranges of applicability. So we'll talk about units here later, but girder spacing in feet, do we meet that range? Yeah. Do we meet the slab thickness range? Yeah. Do we meet the span length range? Yeah. You know, so by and large, most bridges fall within this range, so it's usually not an issue. I mean, if you got something really funky, you're not going to even do this anyways. You're going to do the full-blown model and analysis and all of that. Okay. So far, so good? All right, so let's sort of get into it, and I'm going to start off with positive bending region, okay? All right, so come on. All right, live load distribution factors. All right. Okay, so for the first, so what I'm going to do here is I'm going to say positive bending region, all right? And I'm going to focus the majority of what I do on positive bending, and then we'll go way back and say what happens in negative bending, and not a whole lot. Okay. So the first thing we need to do is we need to compute what's called a longitudinal stiffness parameter. Or kg. Okay, so to compute our longitudinal stiffness parameter, we're going to need a few things, okay? Number 1, we're going to need our modular ratio. And what's our modular ratio? 8. There we go. All right. Now, we're also going to need our moment of inertia and our area, okay? Our moment of inertia and area of what? Okay? It's the moment of inertia and area of just the steel beam by itself. Now, if I go to my spreadsheet, in fact, I might even copy and paste a little bit. Let's see if I can make that work. Okay, so this is the positive. Oh, this is the positive bending region, and I'm going to scroll down a little bit. And here are my section properties for the non-composite section, right? Right here. Let me pull something up. Let's do that. All right, let's take that. Let's squinch it up maybe a little bit. Is that fine? Can y'all read that? Maybe make it a little bigger. That good? Okay. All right. So here's our section. We need the moment of inertia and we need the area. So I propose that the moment of inertia is 15,969 inches to the fourth, and the area is 48.88 square inches. So far, so good? All right. Now, we're also going to need EG, okay? Now, I'm going to write out the definition. You all have it on your slides, but I'm going to go ahead and do it again. All right? EG is defined as the distance from the center of gravity of the beam to the center of gravity of the slab. Okay? So, what do I mean by that? Okay? So here's the slab. All right. If you don't already have it out, you probably want to get out that thing at the end of the section properties handout where we've got the bridge, because we're going to need some of those flange dimensions here in a second. Go down a little bit. All right. Okay. So a couple things. What's the haunch? 2 inches. What's the slab thickness? 8, not the 8.5. There, good, right? We're using resistance. Effective structural slab thickness. So TS is 8 inches. Okay? What's the web depth? What's that? 42? 42. All right, and what's this thickness here? 1.25. Notice how I did not include the top flange thickness, but I don't need it. Okay? Make sense? Because the haunch includes that. Okay. Now, how do I determine Y bar? In other words, the center of gravity for the steel beam by itself. The steel beam by itself. I propose that that is 879.41 inches cubed over 48.88 inches squared. Y'all see where I'm getting that? Well, it is, but I'm wanting you to follow the numbers. Make sense? So sum of AY over sum of A, okay, for the steel beam by itself. So my question is this: how do I get from here to here? And I propose to you that that distance is EG. The center of gravity of the beam to the center of gravity of the slab. And here's how I'm going to do it. I'm going to say that EG equals 1.25 inches plus 42 inches plus 2 inches plus half of 8. Okay? So if I start here at the way bottom, that's going to get me here, 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 and then to there. Then I'm going to come back down, or then I'm going to take that, and I'm going to subtract something from that. What am I subtracting? Y bar minus and plug and chug, you should get what? Ooh, I'm making y'all do math. Oh, woe is me. Here we go, 31.25 inches, right? Something like that, 25, 26, whatever, close enough for more. All right, so far so good? Okay, now we needed that distance because kg is the modular ratio times I plus AEG squared. So that is 8 times, I'm going to do brackets, what was that, 15,969. And then 31.25 inches squared. Get that out of my way. What does that come out to be? $509,627, is that what you said? And like, let's see, 509,627. We don't need the decimals or whatever, that's close enough. Sound good? And that's inches to the fourth. So that's a longitudinal stiffness parameter taking into account the slab and the beam. Does that fit within our range of applicability according to the spec? Of course, yeah, it's almost like smack dab in the middle. So at least I want to make sure of that. Yeah, so 10,000 to 7 million, so we're good. Okay. All right. The little thing there is new. What is that, like something from Minecraft? Thing there in the top right. That's new. Okay. All right. So far, so good? Okay. All right. Now, we're going to do this in categories, okay? And we're going to compute a bunch of these. So, we're going to take it one step at a time. So the first thing that we're going to do is interior girder moment. Okay? Interior girder and moment. Okay? So I apologize if I'm going back and forth a lot, but I'm trying to reference everything to the spec. Okay? All right. So I'm here, I'm in the spec, I'm on page 4-37, which you all have that spec handout, or at least you should. Okay? I'm on table 46222B1, live load distribution factor for moment and interior beams. So that's what we're talking about. Cross section A, here's my range of applicability. 1 design lane loaded, 2 or more design lanes loaded. So single lane loading scenarios, multiple lane loading scenarios, and it's a nice, pretty plug and chug equation. All right. So far, so good? All right. So oh, come on. Okay. So If you want, some people use G for distribution factor. Some people just use DF. No big deal. So I'm going to say distribution factor for single lane loaded is 0.06 plus S over 14 raised to the 0.4, S over L raised to the 0.3. You can tell I've done this a lot since I kind of just remember this. 12 L, actually let me put the decimal, 0.0 LTS cubed, and then kg. But I just remembered that. Okay, now one thing if you're curious about, if you want to be cognizant of your units, okay, if you go to the spec, let's see, so we're in section 4622, which has got all the live load distribution factor stuff. If you go to the beginning of that section, like right here, it goes through and it lines out all the variables and all the units. So for instance, girder spacing is in feet, slab thickness is in inches, and so on and so forth. Does everybody see that? In fact, they're spelling that out because, for instance, if you go to right here, do it again. This, for instance, this 12 right here, that's essentially a unit conversion. Because this is going to be inches to the fourth, this is going to be inches to the third, and this is in feet. So you multiply it by 12 to get inches. That's where that 12 comes from. All right? So plug and chug, 0.06 plus S is in feet, so that's 10. L is what, 90? On the bottom, 12, 90, 8 cubed, and then, what was it, 509, 627. And I'm being a little loose with the units on this because, once you've delineated all your variables in the appropriate units, it all gets washed out. So as long as I know I've got my input correct, I'm good to go. So what's that come out to be? And we'll say 3 decimal places is good. That's what calculators are for. 472. Am I getting something else? My number's a little higher. I want to make sure everybody got this. I got 0. Oh, wait. What's that? Okay, I got this. I got 0.508. It might be 0.509 or 0.507, depending on how that kg was rounded. But don't forget this is raised to the 0.1. Actually, let me clear that. Let me 0.1. Now, I want to make sure. I know this calculation's a little involved, so I want to make sure everybody's getting this. Did anybody get that? Oh, forgot your calculator. What'd you get? 353?
I got it 0.597.
Okay, you got that. Okay, all right. Let's go into Excel. Let's do this in Excel together. So let's make sure we're clear on this. So, all right. I'm actually going to open up a new Excel sheet. Oh, I'm going to try and open up a new Excel sheet. There we go. All right. Oh, okay. So here's how I'm going to do this. I'm going to say equals 0.06, okay? And I get, pretty crazy with my parentheses if I need to. I say it's term A times term B times, I'm going to have 3 quantities. Oh, plus, yeah, plus. All right. Okay, I've got this raised to the 0.4. I've got this raised to the 0.3. And then I need this raised to the 0.1. Okay, everybody with me? Oh, did it not? Oh, whoops. All right. Okay. All right. Now, what do we got? Okay, in here we got 10 divided by 14. Here we got 10 divided by 90, right? And here we got, what is it, 509,627 divided by a quantity. That quantity is 12 times 90 times 8 cubed. Okay, and I'm getting 0.508. All right, everybody good? Did you get 508? Okay, there we go. There we go. That's right, there we go. All right. You don't have your calculator. If you're that good, you need to be doing something beyond engineering or something. You need to be on like America's Got Talent or something. Okay, now for, let's see if I can remember this one. All right. For multiple lanes loaded, let's see if I can remember this. All right. So the equation is arguably, it's very similar, only this becomes 0.75. This becomes 9.5. That's 0.6. Oh, I can clear it up a little bit. That is 0.2. And I need 0.1 up there as well. 12 L TS cubed kg 0.1. How'd I do? I do good? There we go. All right. Now, if I just told you the answer was 0.734, would you believe me? All right, you all can go through and plug and chug, but it'll come out to be 0.734. All right. Where's my little thing? Hand out. All right, so far so good? Okay. Okay. So we've done interior girder moment. Okay. Now what we're going to do is interior girder shear. Okay. So this is where I want one of you all to open up the spec, and I want you to tell me what the equation is. So I'm going to make you dig through the spec and tell me what's the distribution factor for one lane loaded scenarios and what's the distribution factor for 2 or more lane loaded scenarios. Make you dig through the spec a little bit. All right. Okay, we'll get 2 people. All right. So your point, say it again. Was it? 25. Okay, and somebody over here. What's this 2 lane loaded scenario going to be? Anybody found it? All right, I'm on, let's see. Okay, so we're on 437 for moment interior beams. I'm on 443. All right, hold on. All right, go ahead. Minus, there we go. And then that whole thing is 35, there we go. There we go. All right. I always forget to do that. All right. Is everybody okay on where I found that? Everybody able to find that? Okay, so this is on 4-43, page 4-43. Maybe I'll put that up top. Okay, and what do you get? Okay, so 0.36 plus 10 over 25, that's 0.76. And then this is 0.952. Okay, so maybe I should have been clear about this a little earlier, but let's say we were dealing with only interior beams. If you were the designer, which value would you use? What's that?
Higher.
The higher one. That's going to generate the larger moments, which are going to generate more forces to design for, right? You know, worst case scenario, larger loads. Now, since I'm lazy and I want to sort of design all the beams the same way, maybe what I'll do is I'll calculate distribution factors for the exterior girders as well and just design the worst case scenario across the board, okay? So that's why what we're going to do now is let's look at the exterior girders. And we'll just take the worst case moment and worst case shear, and whatever I design for, I know that every beam will work. Make sense? Okay, so now let's do exterior girder. But to do exterior girder distribution factors, we got to take a little bit of room on the side, and we got to do a lever rule analysis. So let's sort of draw a line in the sand. Let's do a lever rule analysis. Okay, so here's how the lever rule analysis works. Okay, so I'm going to draw the deck. Something about like that. Okay, let's put some dimensions on here. Does anybody know that dimension right there? And I like to keep that in inches. What is this dimension? 3'6". So that's no. Okay, that's the total overhang. I'm talking about just the barrier width. That's a good point. Okay, so say it again. 1'6". That's the barrier width. So that's 18 inches. Right? Make sense? Okay. That dimension is going to be important here in a second. Now, what I'm going to do is I'm going to go 2 foot from the edge of that barrier. So we're going to say, 2 foot over, so 24 inches, and that's where one of my wheels are going to go. Okay, so we'll say 1/2, right? And then the truck is going down the road like this, going down the road, and it's 6 foot wide between those axles. So another 6 feet. Or what is 6 feet? It's 72 inches. And I've got 1/2. Make sense? Okay. Now, from the edge of the deck to the exterior girder is how far? Now, somebody else had given me that number earlier. That was the 3'6", right? 42. So that's what, 42? So 42 inches in is where that exterior girder is. Now, just by sheer coincidence, that's actually right under that load because the dimension from here to here is 42 inches. And that just happens to be 18 plus 24. That really truly is a coincidence. Okay, make sense? So ultimately, maybe I should draw it like this. Ultimately, what we're after is this reaction. That's what we're after, right? Now, how far is it to the next girder? What, 120 inches? So, something about like this. And then I've got, I don't know, let's see how good I am with my art skills. What do I got? I got something like that, and then that. Something about like that, right? So far, so good? So let's see if we can do a little bit of math. Anybody tell me what this dimension is? .48 inches. There you go, exactly. Because I know from here to here is what, 162? Take 162 and subtract those, and that'll give me 48. Make sense? Okay. So what I'm going to do is I'm going to sum moments at this hinge to determine that reaction. Well, yeah. You can do that. I'm just, being generic. All right, so far so good? All right. Now, if you've never seen anybody sum moments like this is sort of the way I do it. Credit goes to Kerry Stauffer at Bluefield State, because once I saw him do this, I didn't do it any other way. So I'm going to sum moments at the hinge. Then I draw myself a little table, and I say everything spinning that way has to equal everything that's spinning that way. So I'm looking at this hinge, and I just sort of write my moments where they go. So I start here. I've got this 1/2 generating moment like that, right? So from that hinge, it's at a distance of 48 inches. So I say we've got, at that hinge, we've got, let's see, going like that. That's 1/2 times 48 inches, right? Then the next one is 1/2 at a distance of 120. And then to resist that, I must have a reaction at a moment arm of 120 inches. Make sense? All right. Y'all are probably used to an equation, somebody, choosing a sign convention, writing out an equation. That's just sort of how I do it. All right. So 120R is, what is that, 24 plus 60, 84? 84. So R is 84 over 120, or 0.7. Okay? Make sense? Not too bad, right? Okay. So my lever rule analysis generated a reaction, a distribution factor of 0.7. Or actually, no, I'm saying that incorrectly. All right? My lever rule analysis generated a reaction of 0.70. That's not the distribution factor because we haven't applied multipresence yet. Talk about that here in a second. All right. So far, so good? Okay. All right. Now what we're going to do is we're going to look at exterior girder moment. Okay. All right, so far so good? Okay, so just like last time, we have a distribution factor for one lane loaded and then a distribution factor for multiple lanes loaded. Now, for the one lane loaded scenario, I propose that we take our distribution factor of, or our lever rule analysis of 0.7 and multiply it by the appropriate multipresence factor. So just so everybody's clear on what I'm doing, I'm taking this, which is the lever rule, and I'm multiplying it by whatever goes in here, which is my multipresence factor. All right, I'll give you all a second to write this down and catch up. All right, everybody caught up? All right. Now this is where, unfortunately hopping back and forth between different sections of the code, I know it sort of happens. You got to sort of get used to it. Okay, going back to this presentation. Okay, so remember, multi-presence factors are intended to account for those coincident loadings. And if you've got one lane loaded scenarios, we up our multi-presence by 20%. So since we're talking about a one lane loaded scenario, single lane loading, our multi-presence factor is 1.2. Make sense? Everybody okay? All right. So I propose that this needs to be 1.2, and that makes that 0.84. All right. So far, so good. Okay. Now that's distribution factors for one lane loaded scenarios. For two lane loaded scenarios, this is what we do. Okay? We take our distribution factor for the interior girder and we modify it by a modification factor. Okay? Now, where am I getting that? I'll show you. Okay, so I'm going back to the spec, and here we've got, I'm on page 4-40, distribution factor for moment in exterior beams. Okay, one lane loaded, that's the lever rule. Two or more, we take our distribution factor. What we do is we take our interior factor and modify it by E. What's E? It's this. Okay, so far so good? So I propose this is what we're going to do. All right? Oh, goodness. I propose we are going to take our interior girder distribution factor, which, scroll up a little bit, which was our worst case scenario. We had that, no, we're talking about interior girder moment. So we had 0.508 and 0.734, right? So I propose we're going to take 0.734 and multiply it by that modification factor, which happened to be 0.77 plus DE over 9.1. Now, question becomes, what's DE? All right, so what? Sorry, what? I'm sorry, what? No, we got to define that. Give me a moment. I want to pull it up from the spec. Okay, here we go. There it is. All right. So I'm going back to that section earlier. Remember how it was, girder spacing in feet and span length in feet and slab thickness in inches. Remember that? Okay. So this is on page 4-31. Okay. Now, here I've got DE. I'm looking right at it. Oh. And I'm going to read that out. Okay, DE. Horizontal distance from the center line of the exterior web or the exterior beam to the interior edge of the curb or the traffic barrier. Okay, make sense? So essentially for our bridge, what we're talking about is this dimension right here, the distance from this edge to the center line of this girder. And what is that? 24 inches, although in feet it's 2 feet, okay? Make sense? All right, so maybe what I'll do here is I'll maybe draw a little, I don't know, red dashed line or something. A little dashed line right there, and I'll call this DE is 2 feet, okay? Make sense? You have a puzzled look. You did. No, you got a question? No, seriously. Oh. Yes, yes. I'm talking about physical dimensions of the bridge. That's a good point. It just so, like I said, by coincidence, that load was right over that girder. That load could have very easily been over here or over here, what have you. Make sense? All right. So down here, this comes out to be 0.726. Yeah, okay, so maybe what I'll do, well, let me do this. Let me say 734 times 0.77 plus 2 over 9.1, which is 0.726. I wanted to write it out so that we had it. All right. So far, so good? Okay, so that's moment, okay? Exterior. Now, we're actually forgetting a couple more distribution factors. We've got exterior girder, one lane loaded scenarios, exterior girder, multiple lane loaded scenarios, and then special analysis to be continued. We'll come back and do special analysis. All right. Sound good? All right. Okay. So far, so good. Okay. Now, exterior girder. Shear. Okay. Now, distribution factor for one lane loaded scenarios. I get this from the lever rule also. So 0.7 times 1.2, 0.84. That comes from the lever rule as well. Now, for the two lane loaded scenarios, I say, let's take, how did I write it up here? I said DF for the interior times E, just like I did last time. So now for shear interior, what's the worst case scenario? We had two values, right? 952, right? So 0.952 times E. Now, I want somebody to go into the spec and tell me what that modification factor is for shear. So you're going to look in the exterior girder shear table. So it's going to be later back, like 443, 444, 445, somewhere like that. Okay, there we go. You got it. 0.6 was DE. over 10. There you go. Exactly right. Sound good? So that is 0.952, 0.6 plus 2 over 10. That comes out to be, what is that? 1.04? The whole thing or just the... Really? It comes out over 1?
0.76.
Oh, wait. The whole thing is 0.762. Like that. Okay, all right. Because I was going to say that didn't... There we go. Yeah. Okay. All right. Everybody okay on this? Now, for exterior girders, we have 1-lane loaded scenarios, 2-lane loaded scenarios, and special analysis. To be continued. Okay. So far, so good? Okay, so we've done interior girders, exterior girders, we've done moment, we've done shear. Okay, now all of these calcs, every single one of them has been for the positive bending region. When we do the negative bending region, the only thing that changes is kg. Everything else is the same. So all that's going to affect are 3 values. It's going to affect interior girder moment, so it's going to affect the 0.508 and the 0.734. And then it's going to affect exterior girders. It's going to affect this one, this 0.726 here, because I'm taking an interior girder and modifying. That's it. Everything else is the same. Make sense? Now, we still have special analysis to do, which I'm actually going to wait until next week to do. It's not hard, but I don't want to information overload you tonight. All right, sound good? I am, however, going to leave you with a parting gift. Oh, I know. All right, so okay, so here's the parting gift. This is going to be due in 2 weeks, okay? So we aren't even taking this up next week. So problem 1 is 10 points. I want you to draw the influence lines for the reactions here and here and for shear and moment there. That should sort of dust off some of them structural analysis skills. And then for a 90-foot simply supported beam, determine the maximum positive shear and maximum positive bending moment due to the design truck 25 foot from the left support, which you all should be able to do after the lecture today. It's pretty straightforward. Okay, problem 2, this is the big one. Okay, so problem 2, for that bridge that was in the last assignment in 2A, I want you to compute a complete set of live load distribution factors, basically everything that we did today, and there's going to be more. There's going to be special analysis and some deflection stuff and all of that. Okay, although we're not going to worry about the deflections right now. All right, that'll be part 1. Part 2, I'm going to give you some computer output, like the tables that were in that, like, you know, the truck, the lane, the tandem, all of that. I'm going to give you that output, and then based on your distribution factors and combining them appropriately, I want you to factor the loads and tell me the strength 1 moments, the service 2 moments, strength 1 shears, and all of that. We'll go through that next week, okay? So don't worry about that. So this should probably be one big Excel spreadsheet, so that'll be turned in 2 weeks, okay? Sound good? All right, let me go ahead and give you a hard copy. There's that. And just because I like you guys. Okay, So sound good? Any questions? And we're not done with this. We'll pick it up next week, but we're running out of time and I don't want to get an information overload. Sound good? All right, that's all I got for you all this week. I will see you all next week. Y'all have a good week.